Yeah? Now if I multiply with 5 cube et minus 3, what will I get? 5 raised to 5 sigma square. Right? Plus what will I get? If I do with et minus 4, what will I get? 5 raised to 7 et minus 3. Right? Sigma square. 5 raised to 7 sigma square e and so on. Sure? See, if I take 5 sigma square e out common from this sum, what will I get? So, if I get 5 sigma square e out अगर common निकालूंगा, तो I get 1, right? Plus what will I get? 5 square, right? Plus what will I get? 5 raised to 4 plus 5 raised to 6 and so on, right? Which is equal to what? Which is 5 sigma square into 1 upon 1 minus 5 square. Right? Because that is a geometric series in 5 square. You see the point? That is 5 square plus 5 square square plus 5 cube square plus 5 raised to 4 square and so on. So which means, therefore, that this variance is equal to 5 square sigma square e upon 1 minus 5 square, right? That's 5 square sigma square e upon 1 minus 5 square. That is the variance of yt, which is constant. Only 5, you're right, only 5, yeah. Yeah, only 5. Only 5, yeah. 5 sigma square e upon 1 minus 5 square. Right? This is the point. So, the variance here is constant. The covariance here is constant. Right? So, the covariance here is constant. The covariance here is constant. What can you say about the covariance here? The point is, friends, you see what is this? This is variance of yt, no? So this is 5 sigma square y, right? Because this part is nothing but variance of y. Now variance of y here is constant, so this is constant. The variance of y here is not constant. So the covariance yt and yt minus will also not be constant. It will depend upon t. So we got 3 important ways of looking at this. If you look at model 1, model 2, model 3, model 1 and model 2. Okay, so model 1 and model 3 have constant means. Model 2 does not have constant means. Model 1 and model 3 also have constant variances. Model 2 does not have a constant variance. See, so again look at it this way. I'm sorry, let's recalculate this. So let me write this down here. Model 1, model 2, model 3, right? So I have M1, M2, M3, right? M1 is model 1, M2 is model 2, model 3, right? This has changing mean as a function of time. The first model is a model with the mean changes. Yeah? Okay? That's clear? First model, the mean changes in time. The second model, mean changes in time. The third model, mean is constant. The variance of the second model is constant. In time, sigma square. Yeah? Here, covariance constant, right? Here, yeah? And here, covariance is constant, right? So M3 is unique in the sense mean variance and covariance are constant. They are not functions in time. Such time series models are called stationary time series. Such time series models are called stationary time series. So an AR1 model with absolute value of phi less than 1 is an example of a stationary time series model. Is an example of a stationary. So for example, therefore if you remember, that's why I said when you do a regression, for autocorrelation we said phi was less than 1 in absolute value, right? So I was stationary element. So here M3 is a stationary model. Both M1 and M2 are not stationary. But there is a difference in the way they are non-stationary. M1 is not non-stationary because its mean changes in time. But its variance and covariance are constant. M2 is non-stationary because its mean, variance and covariance all change in time. Right? Now that becomes a problem. So suppose you have got some stock data. Stock returns typically, stock prices typically follow the model 2. They follow a simple random walk typically. Because the stock price today is nothing but stock price yesterday plus an unanticipated random shock. So stock prices typically follow. So if you say that there is a correlation of 0.7 between the price of the stock today and the price of the stock tomorrow, you are not sure whether that will remain constant in time. They will keep on changing in time. Right? So predicting therefore the stock prices becomes a very difficult issue. Whereas you have a stationary time series, then if you look at the data and say the correlation between xt and xt minus 1 is 0.8, then if you know xt minus 1, you can say something about the next value of xt. So if you have non-stationary data, then that becomes forecasting becomes particularly difficult. Secondly, because the mean and the variance don't really exist and the covariance don't really exist, right? The whole idea of using T distribution and F distribution and Z distribution becomes non-applicable. Because what's a T distribution? It's a standard normal divided by the, so it's some data which come from a population with a constant mean, a constant variance, a constant covariance. But if the mean, variance and covariance themselves are changing, then you only can't apply the Z, T and F kind of. So if you have non-stationary data, you can't apply the Z, T, F, I-square, etc. tests to that data. Right, that's one problem. And because the entire data structure is evolving. So you can't, for example, look at the past and easily say something about the future based on the mean and the variance and the covariance for non-stationary time series. And a whole host of macroeconomic time series are actually non-stationary time series. Stock prices, all asset prices, a lot of macroeconomic magnitudes are essentially non-stationary. Right? Non-stationary of the M2 type. This is called non-stationary of the TS class, trend stationary. Because what is the problem? The problem is a changing mean. Everything else is okay. So if you remove the mean from the data, then there is nothing that's going to change in time. Right? So if you subtract the mean from the data, so if you know alpha, you know beta, each value you know alpha plus beta t is the mean. So each value of yt subtract alpha plus beta t, you will get something which does not change in time. So it's easy to detrend the data, take the trend out, and then whatever remains will be stationary. M2 is a more complex process. It's not easy to detrend the data. Right? It's not easy to detrend the data. Right? Okay, but there is no trend really. The mean is not growing in time as a function of time. Right? Because it's structured a little bit weird. Right? Okay, so that's that. And the other serious problem with the difference between the two is, the other very important difference between the two time series, especially the AR1 and the non-stationary time series is, look here, yt is this, no? So yt can be written as alpha t plus E1 plus E2 plus E3 plus E4 plus E5 so on. Yeah? By backward substitution. Whereas this model, yt can be written as alpha plus alpha phi plus alpha phi square so on plus e1 plus phi e2 plus e1 plus phi e2 plus phi square e3 plus phi cube e4 and so on, right? Sure? So now look at the impact of on yt of eq in both the cases. Do you see the difference? The impact on yt of e3 in both the cases. Do you see a difference? What is the difference? dy by dt in the first case will be e3. dy by dt in the second case will be phi square. Sorry, dy by dt in the first case will dy by e3 will just be 1. dy by e3 will just be 1. Derivative of y, dy by de3. If you take the derivative of yt with the derivative with respect to e3, you will get 1. What does that measure? That measures the impact on yt of a shock received 3 periods back. And that's 1. dy by e4 will be what? 1. dy by de5 will be what? 1. So it says that however in the past the shock has been received on the system, its impact will continue to be 1. Whereas in the second model, what will dy by de3? Phi square. What will dy by de4? Phi cube. dy by de5? Phi raised to 5. Phi is a value less than 1. So higher power of phi will be smaller. So it means that in the second process, if it receives a shock, the further back the shock has been received, the less is its impact on the current value. The impact of a shock wears out over time. Whereas in M2, the impact of the shock remains perpetually in the level of the system, no matter how far away the shock was received. Right? So there is an oil price shock in GDP is, for example, GDP is non-stationary. Suppose India GDP is non-stationary and there is a demonetization shock to GDP. Then the non-stationary GDP would mean that the monetary impact shock will remain for all time to come in GDP. It will not go away in the level of GDP. And unfortunately, India GDP is non-stationary. So the shocks which the system receives have permanent impacts. It is growth rates which are stationary, and because growth rates which are stationary, the impact of the growth rate will go away. So the growth rate will come back to its original level. But for the level of GDP, the shock received will have a long time, will have a permanent impact. Right? Okay, whereas with the GDP was stationary, it would mean that if you receive the shock today, the level of GDP, the shock will eventually wear out over time. Right? So it's very important also for an economics point of view to understand whether any particular time series is M1, M2 or M3. M3 is a M3 is a stationary time series. M1 and M2 both are non-stationary time series. But M2 is a more fundamentally non-stationary time series. Because it fails all the 3 requirements of stationarity. Constant mean, constant variance, constant covariance. M1 is non-stationary only because the mean keeps on changing. So if you remove the mean from each value, there is nothing left to change and you get a stationary time series. So that time series is such a pain. But the middle time series, and unfortunately a lot of macroeconomic time series actually follow M2 times. Right? They are non-stationary in a fundamental sense. Right? So we'll look at how that's to be tackled and how does one know whether a given time series is like this and like that and all in the next lecture. Right? Before you do any forecasting with time series and all, you need to understand what their structure is. Whether given time series is stationary or non-stationary. That's the beginning of any analysis of your time series model. So how much time do we have? Oh? What's the time now? Good. You don't have a class immediately?
We have a video.
You're waiting.